So I'm hearing you guys talk about, yeah, the key here is the word rate, isn't it? Where is the rate increasing most rapidly? Because this does sound like a max problem. Actually, there's two ways you can think about this problem. But since we're so close to have been doing optimization, to me, that might be the first thing that comes to your mind. Where is the rate increasing the most is like asking for the max of what? A prime. They're asking for the max of A prime. We haven't done a lot of that. We've done max profit, max this, max that. We've done max of a function. Well, A prime is a function. Where do you look for the max of A prime? When a double prime is 0, when a double prime is undefined, and endpoints. Well, that could be, that number line could be one of the ways to do that, is when it's switching, when a double prime is switching positive to negative. So we would actually do an A double prime number line. Right? So, now this is a calculator one. So, now one of the things I want to make sure you understand, the one we just did, 39, there wouldn't be any work to show that. Right? Now remember, on these packets, these will be handed in. On Monday, or if that's the day we do our first midterm, we will hand in these first two packets. And then the next day, when we do the other day of the midterm, we'll hand in the last two packets. Okay? And that's when I'll go through them. Part of the grade will be kind of an effort, looking at your work and that kind of stuff. Part of the grade will be I'll pick out some random problems that I will check more carefully. Okay? And then that will make your packet grade. And all four of those together will account to about a 25 or so point grade, which would be roughly like a quiz. So it should be a chance for a pretty easy grade, to be honest with you. But, so when you take the midterm, there are a lot of little shortcuts you can do on the multiple choice questions, because multiple choice questions are either right or they're wrong. There's no partial credit. I'm not looking at your work, anything. But on these review packets, the purpose is also to review and to understand the concepts and so forth. And so I need you to be showing your work in these multiple choice questions. Now, the one we just talked about, number 39, there really isn't anything to show there. So I don't care. If you don't show any work there, that's fine. Okay? If you don't show any work on number 39, that's fine. When I go through and check them, I'm going to have notes to myself, and I know, here's a problem you didn't have to show any work. Here's a problem you didn't really need to show any work. But on one like 42, you do. Now, somebody in their class said, well, here's what they did. They graphed A prime, because they knew they wanted the max of A prime. So they just, as a matter of fact, they might have even graphed A. No, I think they graphed A prime. I think they just graphed A prime, and they looked where it was at its peak. And then they just wrote it down. That's not enough. On the actual midterm, if this was a multiple choice question and you did it, that'd be great. That's a great strategy. On the AP test, great strategy. But if that's a free response question, not good enough. You've got to show the calculus ideas that led you to why that's the max. So that's why you've got to do the derivative, and you've got to do the second derivative here, set it equal to 0. You've got to write that down. So when we're doing these packets, I want you to do them like they were free response questions for the most part, as far as showing your work and that kind of stuff, because that's just going to help you. Okay? And unfortunately, every year I get some people who don't pay attention to that, they just don't work very hard at the packets, and they just go through it, and as I leaf through them, I just see C, D, I just see answers short. Okay, that's not enough. On a few problems, it's enough, but most of them it's not. Okay, anyway, so what is A prime? Somebody have it for me real quick? And you could use your calculator, so your calculator could give it to you. I'll use T's, but was that minus 60? And then we need A double prime, which would be negative 24T plus 72. And what we just decided is where A prime is a max is where A double prime is 0. So we're going to set that equal to 0 to solve it, and we get T equals 3. Now, you might be, again, to save time here on the actual test, let's say you did work your way through this. You might say, oh, okay, there we go. The workday starts at 8. This is 3 hours later, so at 11 a.m., and you would be right. That's your answer. But that you're kind of leaving out something. What are we leaving out there? Well, we didn't do anything with endpoints. How do we know that that's a max? What? It could be what? It could be a minimum. or a flat spot or something. All we know is that's where A double prime is 0. That's all that told us. That didn't tell us that's a max. Now it turns out it did, and if this was a, if this was an actual multiple choice question we were doing on the test, maybe for time's sake we'd be willing to trust that. Or maybe we graphed A prime and we could look at it and tell, okay? But anyway, so what you would really want to do is an A double prime number line. And like Sam was saying a minute ago, show that that goes positive to negative, which it does, okay? But it's an A double prime number line because we check where A double prime is 0 because remember we're doing the max of A prime. But now, so there's doing it like a max problem. Now I want to talk about this in another way. Where is the rate increasing the most rapidly? What if I was just doing an A graph? And let's say this A graph went like this. Where in there is the rate of production increasing the most? At the inflection point, right? That's not when we're making the most product. Up here would be where we're making the most product. If A is the number of products, up here would be the most products. But here's where the rate that we're making the products is increasing the fastest, is right there. Well, where do you look? Think of the chart. Where do you look for inflection points? Which is when the A double prime is 0, right? That's when A goes from concave up to concave down, which is when A double prime goes from positive to negative. Look at my number line. Isn't that what I just did? What I just did is found inflection points. I took A, did its second derivative, set it equal to 0, and I checked to see if the concavity of A was changing, which is what this tells me. Same exact thing. On the one hand, I was thinking of it as the max of A prime, but if you think about problem 39, we just got done saying that the inflection points are where the derivative has a max, right? So, I mean, it makes sense that while we were finding the max of A prime, we were also finding an inflection point of A. Really, with the same work, we were showing those two different things. That those two different things are really the same thing. All right, so it is a max and it is 11. And that's what. All right. I can't remember. Was 43 one? That would be worth looking at. Okay. Now, there were a few people in the air class who got this one, but I'm not sure. I think they got it more out of luck, kind of. And then, anybody who want to explain what they did here that they thought was reasonable for getting it? Graphed it? Just graph that function? And then what? Just kind of look to see if there were tangent lines? Now, Tim and I talked about that this morning, and he said he thought there might be 2. He couldn't tell for sure if there would be 1 or 2 when he graphed it. And you're convinced there's just 1. And that's possible. I mean, basically what we're looking at is this. Basically what we're saying is if I've got a function here, okay, would there be a point like maybe right here where the tangent line goes through the origin? But wouldn't it be possible, I mean, if we knew this graph came back up here, wouldn't it be possible there's another one over here? You see what they're asking here? And are there other places on the graph where the tangent line might come back here and go through the origin? Okay? So yes, you could graph it and look at it, and if you were convinced that you were seeing the whole graph on your page and you couldn't think of any others, so there's only one, I mean, yeah, you could probably feel comfortable doing that. Because the other way to do it's going to take some time. So let's talk about the other way to do it. Let's take this one here. Here's how you would actually work this out to tell. Do we know this point right here? What can we call it? A, B, X, Y, whatever. Do we know this point? 0, 0. Huh. Does that look familiar at all? What's it look like? And Luke Skywalker. This is the Luke Skywalker problem. Shanghai, sort of the same thing. What was the key to the Luke Skywalker problem? You got it? We're going to get this. Before long, when I say, what's the key to the Luke Skywalker problem, you're going to have the answer for me. 2 different ways to write the slope. One you learned in algebra class, one you learned in calculus class. What's one way to write the slope? Rise over run, or subtract the y's, subtract the x's, right? That's what you learned in algebra class. What's another way? Derivative. Right? This is a tangent line. The slope of this tangent line can be written as either the slope between those 2 points or as the derivative of this function. But they got to be the same. So one way to do it is to do this. Y minus 0 over x minus 0. Another way to do it is y prime. Those two got to be the same. Okay, so tell me, what can I substitute for y? What's y? No, that was with parametric. In the Luke Skywalker problem here, we had y prime over x prime because that was the formula for slope of a parametric. In this problem, what's x prime? Just 1, because we're doing the derivative with respect to x, so we wouldn't have that. Okay, so let's go back to this. So y minus 0 over x minus 0 has got to be equal to y prime. That's the lesson from Luke Skywalker. So what's y? Well, that's this. So 4x to the 5th minus 3x to the 4th plus 15x squared plus 6 minus 0 all divided by x minus 0 has got to equal y prime, which would be 20x to the 4th minus 12x to the 3rd plus 30x, and you solve that on your calculator. That's how you would want to do this problem. Okay? You will, though. You will. You'd be closer to doing it now than you were a week ago when we did Luke Skywalker. And the more you see of these, the more often you're going to, pretty soon, hopefully, you're going to look at one like this and you're going to maybe draw it. You're going to look at it and you're say, hey, there's a tangent line. You're like, oh, there's another point. Oh, hey, there's 2 points on that line. This is like Luke Skywalker. I need 2 different ways to write the slope. One way is slope between 2 points, which I learned in algebra, and another way is derivative, which I learned in calculus. And those two have to be the same on that tangent line. Those have to be equal. Okay? So now you can get your calculator out, and you can do a solve, and you get one answer. You only get one x value. So there's only one place where this works. And so that's how you would know that. Okay? So the answer is that. All right. Now, I'm not going to, because I want to take some time for some stuff we have to do here today. So I'm going to help you on one more. It's on the free response. It's number 4 or 5. The tower one. Is that 4? Okay. Okay. The tower problem is also Luke Skywalker / Shanghai. I mean, the picture looks a lot like the Shanghai problem. I mean, it looks a lot like it. Okay. Now, the Shanghai problem was a little different in the sense that we had to handle that one a little differently because we didn't know this point or this point. That made the Shanghai problem even harder. Luke Skywalker is actually easier than the Shanghai problem because we knew the rebel base was at 0, -4. And on that last problem, we knew that it had to go through 0, 0. Right? And I think the same thing is true here. We don't know what this point is. Okay, this is xy. But don't we know this point? What is that point? 0, 1/16. Now you've got 2 parts to the problem. One is to write the equation of this line, right? Well, what do you need for the equation of that line? Slope and point. We got the point, 0, 1/16. So all you need is a slope. Well, in the Luke Skywalker problem, we're going to do 2 different ways of doing slope, and we're going to solve for that x. We're going to find that x point, and then we'll know the slope. So then we'll know the equation of the line. And then the next part is from the top of the tower, you're blocked by the hill. What's the farthest out here, or what's the closest you can see to the base of the hill? In other words, you want this distance right here. Well, I think you know this point, don't you? How can you find this point? How can you find this point right here? This point right here? Take your y equation, and that's the parabola, and let y be 0, right? Now you have to solve this without a calculator, so there's some algebra involved here. Okay, I'm not going to go through it all with you, but I will help you individually if you get that. But we let y equal 0 and you find that. I think it's like 200. I think it's like 200. Okay, so what you need to know is this point. Well, if you do part A, if you find the equation of this line, can you find this point right here then? What would you do? Let the y be 0, right? So if you have the equation of this line, so if we can find the slope, if we can find what x is, we can find the slope. If we can find the slope, we can write the equation of this line. If we have the equation of this line, we can let y be 0 and we can find where it crosses. Which is kind of cool because that actually is what we're going to be talking about today. We're going to talk about where tangent lines cross the x-axis. Okay? So a tangent line crosses the x-axis when y is 0. So once you write the equation of the line, you let y be 0, you solve, and you'll have that point, and then you'll know how far it is in between them. And that's what they want. Okay, so the whole key is we got to find out where this point is touching the parabola. So it's Luke Skywalker. So let's get the setup started. So what do we do? I'm ready. I could. Let's set it up first before I do that. Okay, y minus 116 over x minus 0. That's the algebra way we know to do the slope, right? Slope between those 2 points. And I know that's got to equal y prime, right? The derivative of the parabola. And again, here's y down here. Right? Here's the y equation. Okay, so now we can substitute. In place of the y, we can put that equation. So we go 100 minus, I would write that as 1/400th x squared. You guys know how I don't like writing that divide there, because then people start thinking of quotient rule and crazy stuff like that that shouldn't even be a part of that. It's just 1/400th times x squared. So there's y minus 116 all over x. And then y prime would be what? Negative 1/200th x. Okay? Derivative of 100 is 0. This would be 1/400th x squared. Bring the 2 down in front. That'd be 2/400ths, which would be 1/200th x to the first. So those got to be equal. Now this is no calculator though. Right? So yeah, you'd love to put this in and do a solve right now. Right? But you really can't. I'm going to leave the rest of it. I'll just tell you, multiply x over to the other side. Right? Clear those fractions out of there, maybe multiply by something, 400 or something, get the fractions out of there. And then it becomes a pretty easy equation to solve. Okay? But again, that's Luke Skywalker. Slope between the 2 points is equal to the derivative, because the derivative is also the slope of the tangent line. So we solve that. That'll find what x is, so we'll know that point. Once we know that point, we'll know our slope, which means we'll be able to write our equation of the line. We'll be able to let y be 0, we'll be able to find that point, and got it. Okay? So, Luke Skywalker, all over it. 2 different ways to do this one. Okay? All right. So let's set that. I mean, make a little note to yourself, whatever, what you're going to do to go through and finish that. And then when we have some work time on packets tomorrow or next day, whatever, if you want to check, we got the answer book. Remember, this is the answer book. You want to check in there and see how you did and so forth. You can do that. All right. So, go ahead and get your notes out. Now, we may have some time in class to take some more sample 1 questions, but maybe not a lot, because we'll move on to sample 2. So if you've got other ones, find a time to get in and look at this. Find a time to get in and talk to me. Okay? Sometimes we spend our class time on the hardest ones. The ones that a lot of people couldn't get. But then there's always those other ones that, some of the people, number 15, maybe some people over here couldn't get, but everybody over here thought it was easy. And then number 23, you guys all thought it was easy, and these guys all thought it was hard. So we don't want to go through every single one of them. But there are some that you'll want to talk about. Just don't be thinking that, oh, geez, nobody asked about 22. They all thought that was easy. I thought it was hard. Well, then come ask me about or ask somebody about it. Get that figured out, because you want to make sure as many of them are as easy as possible. Remember, the midterm scale, you get over 55, 60%, you're going to get an A. Probably, right? You get above 60%, you got an A. Okay, so you want to get as many of them that you can do as possible, right? To pass the test, you probably need, passing is probably somewhere in the 20% range. You know, I mean, so, you know, yeah, basically. So, I mean, but that's the way the AP test. So, yeah, so that understand, some of them will be different, no question about it. But you want to find this, you want to get good at as many of them as you can. All right, so you can get that up there as best you can. All right. It's funny with the with the midterm and the final. It seems like there's kind of two extremes. Some people get too nervous about it because they work through these packets and they're so hard, and they can't come up with a lot of them, and they think, you know, geez, I don't know any of this stuff, and they worry too much about it and forget that, hey, there's a scale. And so usually the class average is higher than our normal class average. The quiz we took Friday, the class average was about 72. Now, to be honest, that's fairly normal most years for a lot of quizzes. For that one in particular, that's pretty normal. Nice thing is this year that's a C, where last year the class average was a D. But, I mean, you know, so that's good for you guys. But that's pretty typical, okay? The average on the midterms is usually higher than that, probably pushing 80. Okay, so that's a good thing. So it's not something, the midterms aren't something to get overly freaked out about. Then we have people on the other extreme that think, oh, great, there's a scale. That'll be great. I don't have to do anything. I don't have to work at all. You know, I'll get what I normally get, and I'll get the benefit of the scale. Well, probably not. If you don't spend much time in these packet problems other than what we do in class, 20% might be where you're at. Okay? So, you know, we gotta spend the time. All right. So you want to find some middle ground. We're going to talk about this thing. I got it written on the board up here, but we're going to talk about this thing called Newton's method. Okay? Now, what Newton's method is a method for finding the roots of an equation. What are the roots of an equation? Where it crosses the x-axis. Now, this is an old technique that kind of we would never have learned at the high school level. I never knew about Newton's method until I started teaching calculus. Never learned it in calculus in high school or in college. And part of the reason was there were just too many hand calculations to make it worth doing for that level. But hundreds of years ago, you know, engineers and mathematicians, people like this, had to do, I mean, they spent a lot of their time doing hand calculations or looking them up in tables. If you had to know the square root of 2, you'd go to a square root table and you'd look up the square root of 2. Most people then would know the square root of 2, but if you need the square root of 437, you'd go to a table and look up the square root of 437. We would grab our calculator and do that. Basically, we have an electronic table instead of a paper table. Okay? But somebody had to make that table. Somebody had to calculate the square root of 437. How did they do it? Right? How did they do the square root of 437 or whatever? Let's say it's square root of 39. Make it a little easier one for us. How would we calculate the square root of 39? Well, one way, it's kind of funny, we don't do this anymore either. Again, I'm not that old, but I'm old enough to remember before calculators were real widely available. And when I did my first observing in a classroom in college, I went to an 8th grade class, and they were working on doing square roots by hand. You guys probably never had to. Let's say we were doing the square root of 39. Here's how this 8th grade class was doing the square root of 39. You don't need to write any of this down. They were doing something called the divide and average method. So here's how it would work. Square root of 39. They would start with a guess. What's your guess? 6. 6 point something, but let's start with 6. Find something reasonably close. So we would start with 6. And so here's what they would then do. They would say, okay, if my guess was going to be right, then 39 divided by 6 should be what? 6. right? So they would divide it out. So they would do long division. So they would say, okay, 6 into 39 is 36. 3, bring down the 0. 6 into 30 is 5. So 6.5. So what did they just learn from that? It's not 6, but what else? It's somewhere in between 6 and 6.5. Because if I would have divided by 6.5, I would have got 6. So it's somewhere between 6 and 6.5. This is why they call it the divide and average method. So I would divide, and now I would average these two, and let's 6.25. Now I might not want to start with 6.25. Well, let's do it. You guys are going to have to help me because I'm, you know, I don't want to do these hand calculations any more than you guys do. So get your calculators out. But we'll divide by 6.25. But this is what these 8th graders were doing. Okay? This was a lesson that they were on. So now we're going to divide 6.25 into there. Well, you know how this works. We got to move the decimal over 2 places, move the decimal over 2 places. So now they're going to go, okay, 625 into 3,900, and they had to do this all by hand. So they were doing all these hand calculations. Well, what's 3,900 divided by 625? How much?
It's about
6.24. Okay, so they would have got, well, they would have done, whoops, they would have done 6 here. So what's 625 times 6? Do that one. What's 625 times 6? No, not 6, 625 times 6. 3,750? Okay, so we subtract there, and that's what, 150? Bring down the 0. So 625 into 1,500, what's that, twice? So what's 625 times 2? 1,350? Is that right? No, 1,250. 1,250. So subtract, what's that, 250? Bring down to 0. 625 into 2,500. 4? Yeah, try 4. Oh, it's exactly. Okay, that's nice. So now 6.25 and 6.24. I'm getting close, aren't I? Divide and average. What's the average of those?
6.245.
So I would be comfortable that I'm at least right out to 2 decimal places at this point. Now, what is square root of 39? Has anyone done that for me yet? 6.244 something. But I would feel pretty good that the square root of 39, I'm at least accurate at this point up to 2 decimal places. It's 6.24 something. Because it's got to be between 6.24 and 6.25. That was called the divide and average method. We don't teach that anymore. Because we got square roots on our calculators and so readily available, it's not really necessary. But this would have been, well, a while ago, that I was in this 8th grade class, and this was in the textbook, and this is what they did. The divide and average method for square roots. Okay? Now there's another way to do the divide, or excuse me, there's another way we could have done that. This would have been something they could have done years ago. But it works. It's pretty cool, but it takes calculus, so 8th graders wouldn't be doing it. But it'll work not only for that situation, but for a whole bunch of other situations as well. And here's how this would be. What is the root of this function right here? Square root of plus or minus square root of 39, right? The root of this is where x squared minus 39 equals 0, which is at plus or minus square root of 39. So another way to do this would be to find the roots of this function and see what that is, and that would also be the square root of 39. So this would be another way to find the square root of 39. It would be faster than the divide and average method, I don't know. But here's what this method will also let us do. What if you had this function? 3x to the 5th minus 2x cubed minus 15. And we wanted to solve that equation. We wanted the roots of that. Does anybody know how to do that? Is there any way to do 5th degree equations, solving, that you know of? What have you learned all through your algebra careers? What kind of equations did you spend a lot of time solving? Even before quadratic. Linear. 1st degree, right? Geez, variable on both sides, right? Solve for x, get the x by itself. Those are linear equations. You learned all ways of adding to both sides, and you spent years doing that. Then you learned about quadratics, factoring, quadratic formula, right? Solving quadratic. But once you get to cubics, you can't do it, right? Cubics, fourth degree, fifth degree. What about e to the x and sine equations? I mean, if I gave you sine of x equals a half, you could solve that. What is that? Pi over 6, right? That's pi over 6. Or multiples of 2 pi added on to pi over 6, right? So we can solve that, but what if this would have been, instead of 1/2, what if this was 5/7? Use your calculator, right? But now 100 years ago, before calculators, how in the world would we solve some of these equations? So there's a lot of equations that we didn't know how to solve. How did they solve them back then? And how do the programmers on your calculator, you guys love that solve thing, you go solve and you haven't solved it. How do the programmers on the calculator do that? I mean, right now it seems like magic, right? You just type it in and out comes the answer. It's magic. How did the programmers program that thing to give you those solutions? Well, it's really kind of cool, and it's really not that hard when you think about it, okay? So we're going to go through that, and that's this thing called Newton's method. Okay, so what we're going to do, let's back up one here. So we're going to solve this equation using this thing called Newton's method. Now, what's Newton's method? It's finding the roots, finding where the function crosses the x-axis. Okay, finding where the function crosses the x-axis. Now, we know this one's going to be at square root of 39, which we just learned was 6.244 something. Right? That's actually the solution to this, and it'd be plus or minus. Okay? We're going to show how we're going to come up with that here. All right? This is called Newton's method. All right, so here's a function. Here's a function. And it crosses the x-axis a bunch of different places. All right? So here's what Newton's method says. First, we start with a guess. Okay? Just like we were doing with the divide and average method. We start with a guess. The second thing we're going to do is we're going to plug that into the function, because what are we hoping happens? Yeah, and what would happen if it's right? But what would we get? We'd get 0, right? If my guess is correct, when I plug it into here, I'll get 0, right? So I would put in a 6. 6 squared is 36. 36 minus 39, oh, it's -3. It's not 0. So it wasn't right, okay? But that's the first thing we do. So we will come here and we will plug in, make a guess somewhere in here. We'll plug it in. Oh, shoot, we didn't get 0. Okay, we didn't get 0. Now, here's the thing we're going to use. Remember what we learned about tangent lines? And right in this area, the line and the curve are basically the same thing. Remember that? The line and the curve are basically the same thing. And what we're talking about now, oh, whoever's watching this isn't good to see this. What we're talking about now is right here where the curve is crossing the x-axis. If I had a tangent line right near here, wouldn't the line cross the x-axis pretty much the same place the curve does? But the difference would be a line is a linear equation. We know how to solve linear equations, right? Think about the tower problem we just did. If I could take the line equation, set it equal to 0, see where the line crosses the x-axis. That'd be pretty close to where the curve crosses the x-axis, if my point was pretty close. If I could get a point that's pretty close to there, right? But of course, that's a whole difficulty. I don't know what that point is, right? If I knew what that point was, I wouldn't even do this, right? But what I would like to do is I would like to get, what I would like to do is I would like to get a tangent line that's really close to one of these roots here. Now remember, this is 100 years ago, so I don't even know what the graph looks like, maybe. Right? It was hard to even draw graphs of these complicated equations. Now, x squared minus 39 is not a hard one to draw. But, right, these are kind of hard to draw. So we're using this as a visual aid, but remember, we wouldn't really have this graph in front of us. So we got to imagine in our heads that we're doing this with just the equation we're looking at. All right, so we're going to make a guess. And we're going to plug it in. Because even if it's a complicated equation, I can take a... Why does it keep doing? I could take even with a complicated equation, 5th power or sine, I could take a number and plug it in and work that out. I mean, if I had to do 6 to the 5th power, I could do that without a calculator. It wouldn't be a lot of fun, but I could do it, right? Okay, so we're going to take our guess, we're going to plug it in. Now, here's the thing. We're going to now write the tangent equation to that point. Now, what do I need to write the tangent line? Slope and point. Well, I got the point. That was my guess, right? I took my guess, I plugged it in, so I got the point. Now I need the slope. How do I get the slope? Derivative. And even hundreds of years ago, we knew how to do derivatives, right? We knew how to do the derivatives because we have the rules. You guys just did a gateway test with no calculator, right? You can do derivatives without a calculator, right? So that was easy. So we do the derivative. We plug our guess into the derivative. That would give us our slope and our point. We'd write our linear equation. Okay? And then we would see where that crosses the x-axis. And how would we do that again? How would we find where our linear equation crosses the x-axis? Set it equal to 0. But it's a linear equation. We know how to solve those. Those are easy. So we would find that point right there. What do you suppose we do with that? Plug that back into the original. Hoping what? Hoping it's right. Hoping we get 0. Shoot, we didn't. Okay? What are we going to do next? Do it again. Let's write the tangent line at that point. Now you can see why we didn't do this back when I was in school, because this would be by hand. This would be a lot of calculation. It'd be taking a guess, plugging it into a function, might be a complicated function, so it'd be hard to find that point. Then I'd have to do the derivative and plug that point into that. I'd have to find that thing without a calculator, and that'd be a slope, and that'd be kind of messy. Then I'd have to write the equation of that line, which would be kind of messy, and I'd have to solve it. Set equals 0, and that'd be kind of messy. And then I have to plug that, you know what I'm saying? So without a calculator, this would be kind of tedious. But the engineers of 200 years ago, whatever, they didn't always have a choice. Somebody who was making up these table stuff, that's what they did. They had to do these hand calculations. Okay? Not high school kids, but I'm talking about people that needed these kind of calculations. Okay? So this is what they did. You've seen Apollo, we talked about this, Apollo 13 and the guys with their slide rules in the movie Apollo 13. And these guys do all these hand calculations, and Tom Hanks and those guys up in the thing doing all these hand calculations. They had to. I mean, that's what they had. Okay? All right. So now we plug that back in. So what I really want you to focus on is the ideas here, not so much the calculation. All right, so we're going to do it again. We're going to write the tangent line. We're going to see where it crosses. We're going to plug it in, see if we get 0. No, we didn't. We'll do it again. Ah, but look at that line. That's getting pretty close. Where that tangent line crosses 0 is really close to where this black one is, and I'm running out of room here. If I did it again, don't you suppose x5 would be in there even closer? And x6 and x7? And pretty soon, what would you notice about x5 and x6 and x7 and x8? They'd be closer and closer to each other, right? Not 0. They'd be getting closer and closer to each other. Now, when we plug them in, yes, they'd be getting closer and closer to 0. But x5, x6, x7, x8 would be getting just zooming in right here. They'd be getting closer and closer to being the same thing. Okay, let me change my original guess to make a better guess, because what you notice there is my first guess was a bad guess. The tangent line shot me way over here. My first guess wasn't anywhere close. What if my first guess would have been a little better? It would have been close to the 0. Now look what happened. Plug it in. Oh, didn't get 0. Let's make the tangent. Okay, there's x2. Now let's plug that in. Now let's do the tangent. There's x3. Look at x2. x2 is 0.54. Now it's negative 0.06. Of course, this 0 is our root. And now x3, we're getting it, right? We got it. We actually got it. We're getting 0. I mean, we found it to a couple decimal places at least. See, that's what would happen if you have a good guess. Now, when we had a bad guess at first, we were up here near this peak, and that tangent line shot us way out here, right? And the closer and closer you get to that peak, the worse it would be. What if you guessed right at the peak? It would just go across. It would never. That would be the worst guess of all. Is if you guessed right at the peak, and it would just never, ever, come down and touch the x-axis. So, but hopefully that wouldn't happen. That's the idea of Newton's method. And again, think about it. It's very much what calculus is about. Taking something we don't know how to do or solve, and putting it in terms of things we do know how to solve. All right, perfect. So let's think about the key to Newton's method. The key to Newton's method is writing the equation of a tangent line. You don't have to even write this part down, to be honest with you. Well, yeah, you probably should. You probably should write this part. Okay? Because one of the things I want you to get out of this is the ideas behind what's going on. Okay? All right. So we want to write the equation. So all those different tangent lines we were writing. Okay? We needed the point. Well, remember, how did we start? How did we get our first point? We guessed. So we're going to call our guess x sub 0. That's going to be our guess. So the first point we have where we do the tangent, we're just going to call that x sub 0. And what would its y coordinate be? We could use y, but let's use function notation. So f of x sub 0. So there's our point on our tangent line, is that, right? And then what would be over here? This is the slope. What would be our notation for the slope? F prime of x sub 0. Right? This would be the tangent line equation of what I'm doing. Now, what do I care about the tangent line? I want to know where the tangent line does what? Crosses the x-axis. When I talk about Newton's method, a lot of times I talk about writing the tangent line. What we're doing is not writing, but riding the tangent line. We make our guess, we plug in our point, we ride the tangent line down to the x-axis. And then we plug that point in, we do a tangent line, and we ride that tangent line to the x-axis. And we keep doing that over and over again. All right? So what we're going to do is we want to find where this tangent line equals 0, right? Where does it cross the x-axis? And we want to solve that for this x right here. So tell me what I would do to solve this, to get this x by itself. Go ahead. Subtract this, right? Okay, so I would have f prime x sub 0, parentheses, x minus x sub 0, and over here I'd have negative f of x sub 0. Correct? All right, then what? I'm trying to solve for this x right here. Divide by that f prime. So I'd have x minus x sub 0, and over here I'd have negative f of x sub 0 over f prime of x sub 0. Right? And then what? Add the x sub 0 over. Now I'm gonna do something here. If I add this x sub 0, I couldn't stick it on at the end, but I'm gonna stick it in the front because I got this negative, and so that'll make it a minus. Are you with me there? So I'm just gonna write this as x sub 0 minus, and then f of x sub 0 over f prime of x sub 0. And that would give me what? Let's go back to our picture here. Oh, they called it x sub 1. Okay, so this would be like my x sub 0. They called it x sub 1. And I plug that in, I ride the tangent line down to there, and what's that give me? X sub 2, right? So here's x sub 1, my first guess. Plug it in, that's f of x sub 1. I do the slope, which would be f prime of x sub 1. Gives me my tangent line. I set that equal to 0. I find where it's equal to 0, and that's called x sub 2. So back in our notes, what would I call this x I just found? X sub 1. Right? My guess was x sub 0, and I do this. But think about that. That's pretty easy. That's a pretty cool little formula right there. Instead of having to find the tangent line every time and solve it, what I did is I just solved it in general. And my x sub 1 is just this. I got to take my guess, plug it into f, which I'll have because I'll be given that in the problem. F prime, which I can do. If I have f, I can do f prime. I just take my original guess, plug it into f, plug it into f prime, and plug it into this formula. And that gives me x1. And then what do? Do it again. Then I do x1 minus, and then I plug x1 into there and x1 into there, and then that give me x2, and I just keep going, keep going. So here's your formula for your notes for Newton's method. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. And we keep doing it until what? No, not until you get 0. Until the numbers you're getting out, the x sub 5, x sub 6, x sub 7, until they are the same thing. At least out to however many decimal places you want to have. Think about that divide and average method. We keep doing it. We did it until we had like 6.24 something. And if we only wanted 2 decimal places, we're done. If we wanted 5 decimal places, we'd have had to keep going. But at some point, those x sub n plus 1s, x sub 2, x sub 3, x sub 4, x sub 5, they're getting closer and closer to being the same thing. And once they are, you got it. What you have is where that function crosses the x-axis. And if you think about it a couple hundred years ago, this is pretty doable. They would have a function that they wanted to know where it crossed the x-axis. They would start with a guess. They could do the derivative. They could plug in. Now, if it was a complicated sine function and they had to plug 0.579 into a sine function, they'd have to go to a table and they'd have to look that up. But they could do it. Okay, they could do it. There was no way to solve the equation. It would have some complicated calculations, but they could do it. But when I was in high school, it's complicated. The calculations were too complicated to even mess with doing it, so we didn't do it. Now that we got these things, we can do it. Okay? And, matter of fact, we still don't need to because we got the magic solve, and the solve will just do it. But somebody programmed that in there, and this is what they use. Okay? And now there's some other parts to it. How do they get the guess? Because you don't have to type in a guess when you solve it, right? It just gives you all the solutions. So there's some other things going on in there for them to tell what the guesses are. Okay? But this is what we're going to have. All right, so now let's go back to our example with square root of 39. All right, our example was square root of 39. And what we want to do is we're trying to find the zeros of this function right here. Okay? Which we know is going to be 6.244 something plus or minus. Right? All right, so according to Newton's method, we would need to do what? We need to start with a guess. What do you want to start with? 6. So we would have to do 6 minus what? 6 minus, what was the formula? What was the formula? F of 6 over f prime of 6. That's what we would do. Okay? And let's do that. So now we'll cheat here a little bit. And who is my presenter? Steve. Okay? So what I want you to do is we're going to go 6 minus. Now, there could be some shortcuts because there's some keys we can use on the calculator that would be helpful. But for right now, we'll do it kind of a longer one. 6 minus, and now do your fraction. And then we're going to plug 6 into the function, right? F of 6. So you're going to go 6 squared minus 39. Right? And on the bottom, what's the derivative of this? What's f prime on this one? 2x. 2x. So we're going to plug a 6 into that. So 2 times 6. Well, do 2 times 6, and then I'll show you why. Okay? And then hit Control Enter because we want decimals here. Okay, we got that. Okay, now what do we want to do? Now we want to plug that in. So, again, okay, grab that, minus, okay, hit enter, we get that, right? It's kind of what we were getting when we did divide and average, right? Same thing. And then we do it again. Now, at some point here, typing it in, you're going to get more and more decimal places, so typing it in gets to be a pain. So you can kind of go up here and grab that, although that gets a little bit complicated too. So I want you to look on your calculator and see where the negative key is. You got that button that says answer. You know what that means?
The last answer.
It takes your last answer. Well, isn't that what we want here? We want to take our last answer. So what we could have done here is we could have done answer minus answer squared minus 39, all over 2 times answer. And now here's the really cool part. Now you can just keep hitting enter. You can just keep hitting enter and it'll always go back and grab that previous answer. Now look what's happening. We have now found it all the way out to a whole bunch of decimal places. Now, if you think about this, that's pretty powerful stuff with just a pretty easy idea. I mean, this tangent line, and all we did was solve the tangent line equation, and this little formula just simply came from y equals m times x minus x point plus y point. That's where it came from. Okay? So if we can do a derivative, and we can do this. So let's do a more complicated one here. Let's take and show how we could do this one. Here we go, right here. So let's say this was your function, okay? So write this down, 3x to the 5th minus 2x cubed minus 15. Okay? Now let's pretend, and I tell you what let's do. Let's just write this down. Let's don't do anything on our calculators yet. Let's pretend we're 100 years ago. And we're not going to write anything down. We know it's a 5th degree equation. So it could cross several times. It's got to cross at least once, doesn't it? The 5th degree, it's got tails going opposite directions. So it's got to cross at least one time, right? Might cross more. All right? But, so let's look at this. So we want to start with a guess. Now, where you could make your calculator do some of this work for you, I know we're cheating by using the calculator. I just said we're going to pretend we're 100 years ago. Not quite, okay, is I could define f here, the f function to be my f, and then like g to be the f prime. You see what I mean? So let's do that. I think that could even shorten our work a little bit. Instead of having to write all this out, answer to the 5th, 3 times answer to the 5th minus, right? I mean, we could do that. But this might be even better. So let's define. So you can either go to menu or you can just type the word define under actions, menu and actions. Yeah, or you can type it. It's probably faster. Define and then a space and then f of x equals, and then that function we just wrote down. Now this is what I'm calling the shorter way to do it. Now tomorrow I'm going to show you where I'm going to make I want you to write out a table for these various parts of Newton's method and write this out. We kind of ran out of time in the other class, so we're going to save that for tomorrow. But that's something you're going to have to do on the take-home quiz. Is kind of a longer written out version. Okay, but this is kind of the calculator shortcut. Any of these things that we're doing here are kind of calculator shortcut using this Newton's method formula. All right, so go ahead and hit enter. So that defines f of x. And let's define g to be the f prime. Okay, so define g of x. And here's where you could let the calculator do the derivative for you, or this one's so easy, we just probably faster than do it ourselves. So what do we got? 15x to the 4th minus 6x squared. Oops. Okay, go ahead and hit enter. So, all right, so now there's our f and our f prime. Okay, according to the Newton's method formula then, we start with what? What do we got to do first? We got to guess, right? We got to guess. Okay, so where do we think this function is going to cross the x-axis? Somebody give me a number. Where do you want to guess? 1.5. Okay. So here's what you got to do. You first have to, if you want to use the answer key, right? We'll use the answer key. We need to plug in the 1.5 first. Now, let me show you two ways. One way where we don't use the answer key. So let's just type in Newton's method. So Newton's method, we would do what right now if we were starting with 1.5? 1.5 minus, and then a fraction, f of 1.5, and then on the bottom, g of 1.5, because that's f prime, right? We define g to be f prime. And then hit enter. Okay, now what? Now, without using the answer key, we can go up and grab that, because now we want to take that. God, that was a really good guess, by the way. Because look, what do we know about We think we're pretty close. I mean, right? It gave me something that's pretty darn close. Had you cheated?
No.
Okay.
My calculator was up there the whole time.
Yeah, well, that's true. Yeah, you couldn't have cheated. All right. So go ahead. Go ahead. So we can go and grab that. That'd be that minus fraction f of that. Yeah, you're right. We can do answer right now. I'm sorry. Right. Oops. Yeah, now we're really in trouble. There you go. Well, oh yeah, see, we can't go up and grab that. Right. Because your cursor has to go up through there to get there. So you're pretty much stuck with answer. You might be able to use the mouse or copy and paste. Yeah, copy and paste. There you go. So there's a lot of different ways to make this work. Okay, there you go. Copy and paste. And then we get that. Now, what do you know about the answer we're looking for? The root of this function. Look at the last two answers. 1.48. Wouldn't you be convinced though that if you only needed 3 decimal places, it'd be 1.483? Yes. Okay. Now let's show the really fast way to do this. And here's a really fast way to have done this: would have been to type a 1.5 and just hit enter. Type a 1.5 and just hit enter. Your guess. Put your guess, just enter. Now why did I do that? To put that in the answer, because answer is just a variable. Right? So what I just did was put 1.5 in the answer. Now he's going to do answer minus f of answer over g of answer. And now he's going to hit enter, and then hit enter, and then hit enter, and then, man, we can go. And you hit enter a couple more times, well, you're there. Okay? That's how this works. But what is it? It's Newton's method, and it's just writing the tangent line and doing it again and doing it again and doing it again. And having to do all those calculations by hand would be a real mess, but it's pretty cool seeing it in action there. Now, is that the only one? See, that's one root. This thing could have 5 different roots. How would we tell? How can we see if there's another one?
Guess.
Make a new guess. So let's make a new guess. 7. So guess 7. How are you going to do this? 7, enter. And then answer minus f of answer. Now remember, this only works if you get a new function. You have to define a new f and a new g, right? Because you have to have f and f prime. But now he's going to do, whoops. Now be sure and hit control enter here. You're going to get fractions, and we don't want fractions here. Okay, hit enter again. Now slowly. Okay, look where we went. We went from 7 to 4 something to 3 something. Okay, to 2 something. Now hit enter again. To 2.3 something. Hit enter again. 1.94. Keep going. What are we going to end up at? That same one. Okay, 7 didn't give us a different one. Okay, let's try another one. Negative 20. Make negative 20 your guess. Done. A problem where I say use Newton's method too. Okay. So there you go. So what was this first one? Look at that.
It was a fraction.
Oh, it was a fraction because you forgot to hit control enter. Okay. So control enter. So negative 12. So we start at negative 20. Negative 12. Negative 10. Negative 8. Keep going. Hit it fast. Keep going. Keep going. Keep going. Keep going. Ooh, wow.
They like resets. Yeah, mine does that too. It does that over and over and over. That's crazy. There we go. Oh, it's getting closer.
Look at that. It's back to that same one. Now, has anybody graphed this one at all? That's probably the only root. There's probably just one root. This is probably a 5th degree because it had a minus 15 on it, remember? So it was down below the x-axis quite a way. So it might have had a couple of humps and then finally came up and shot up this way, and it hit that one time. But now, something we'll talk a little more about tomorrow. Okay? Oops, keep forgetting. Something we'll talk a little bit more about tomorrow. This is in your book where they talk about this. Remember we said a little bit ago that what would have happened if our first guess was right here at this peak, right? Well, it just would have been horizontal, and we never would have found a root at all. We'd have gotten undefined. Here's another thing that sometimes happens. You make your first guess, and I'm gonna have to kind of cheat here to make this work. But you make your first guess, and the tangent line takes you over here somewhere. Okay, whatever, like this, and then you look at that tangent line, and it takes you right back to there. And then that gives you that, and then that takes you right to there, and then that takes you back to there, and it just keeps bouncing back and forth. And it just cycles, and it's never going to zero in on the root. Now, again, that'd be kind of unlucky to make that guess, where that would happen. Okay? Yeah, you know, and so, but those are, so Newton's method is not, there are some times where it could fail. I mean, obviously, if your tangent line is horizontal, it's never going to go down across the x-axis. And you could get this cycling thing where just the tangent lines would just cycle back and forth between those two. But we were getting one there. What was happening there? Now, think about what was happening. It was shooting us off over here somewhere, and then that tangent line was shooting us back over here, and then that tangent line was shooting us around there, and then we kind of cycled around. It looked like we were getting something, and then all of a sudden we shot off somewhere else, right? And then eventually then it started zeroing in, right? Literally zeroing in on the z. Okay, 1.4. But years of practice. That's an old joke. So, but anyway, that's the idea. Okay, but it's nice. Think about how many calculations that would have took, you know, with that. Yes, I mean, because I don't know how many times we hit that thing. 30, 20.
I got all the way down to 90. Yeah.
Oh, really? I mean, that was a ton that we were getting that ton of. Okay, so on your homework for tomorrow, the only problem you have in the book to do is in section 4.6, number 15. And what you'll do is you'll do that calculator stuff on it. It'll give you a function. It'll give you, well, what it'll do is it'll say find all three of the roots. There's 3 roots. But I want you to be able to go through this method of doing it. So I want you to make a guess. Now, if you want to graph the thing first, see where the roots are so you can make a reasonable first guess. But it might be kind of fun to do what we just did. Just pick some numbers and see which one it gives you. Pick a number and do it and see which one it gives you. That'll be one of the roots. Then pick another guess and see if it gives you that same root or a different one. You know there's going to be 3. So, okay, so, but there's a couple parts to 15. So one of the parts is find the 3 roots. So do it that way, guessing and using the answer thing. Another part, listen up now. Another part of number 15 says, what happens if your initial guess is this? Well, that's easy. Just do that. Do it. And then it says, what happens if your initial guess is this? And then they ask you, what's going on? What's happening when that happens? So that's not going to take you very long. Okay? Matter of fact, you got 6 minutes. You'd probably be done if you really want to. But that part of the homework's not going to take you very long. Okay? The rest of the homework is sample 2. Get going in the sample 2 pack. Okay? Probably that first section, those first 28, the circled ones, you know. Try to do a whole bunch of those. If you could get through that first section on sample 1 or sample 2, that'd be pretty good. Okay? Since it's such a short book assignment, this would be a good night to be trying to get a lot of sample 2 out. Okay? Well, sample 1, sample 2 will be turned in 2 weeks when the first day we do our midterms. But we'll be moving on to the next sample packet, the next sample packet. You know what I mean? Last thing you want to do is before the midterms try to catch up with 4 different packets. So you want to stay caught up. Okay?
Oh, I see it. It's his lucky pearl. The desk is like.
Okay, you can turn the hats back in.
He's so lucky to have this look.
Mr. Clark, I'm not
Yes.
going to be here tomorrow. So
Okay, we'll be doing, there'll be a video about it, but we're going to be doing the